Hello everyone, I hope you are doing great. In this tutorial video, I want to talk about Surface Plasmon Polaritons, and we will do the simulation with the COMSOL Multiphysics. I hope you subscribe to my channel. Please share my channel, leave your comments in this tutorial video, and like this video. Let's start. At first, the electromagnetic waves that are confined to propagate along a surface, such as Surface Plasmon Polaritons, are great of research interest. And because they are interested in the nanoscale manipulation of light. In this model, we want to discuss about the simulation and visualization of the propagation as well as frequency versus propagation constant dispersion relation of SPPs. For the physics background, it's better to know about propagating electromagnetic wave that is consist in a variety of forms such as plane waves, spherical waves, Gaussian beams, and so on. There are also propagating electromagnetic waves that are confined in a space such as waveguides and waveguide modes propagating in metallic or dielectric waveguide. In addition, there is another special type of electromagnetic wave that is confined to a planar surface. This type of wave propagates tangentially to the surface with exponentially decaying fields in perpendicular direction. Its wavelength is often smaller than the free space wavelengths at the same frequency. Thus, this type of wave provides promises for nanoscale control and manipulation of photons, which is desirable in many applications, ranging from optical communication and information processing to solar energy harvesting and digital displays. The existence of this wave type was found at metal dielectric interfaces and is known as Surface Plasmon Polariton. The term plasmon refers to the collective oscillation of charge in metal, whereas the term polariton generally refers to a quasi-particle that is the result of the coupling between a photon with a polar exciton in a material. The SPPs are the result of coupling of surface plasmons and light. Here, as you can see this geometry, we have two different materials, dielectric and metal, that we want to demonstrate the SPPs in the simplest system that we can call it the bulk metal dielectric interface. We can imagine that the metal dielectric interface is represented by the XZ plane at y equal to 0. The dielectric region is above this y0, and the metal region below of this plane. And here we must consider the equation that it is our interest that study the TM mode surface wave, that the expression for the electric and magnetic field in the dielectric and metal are given by equation 1 to equation 4, this equation, and where D is the denote the dielectric and M is denote the metallic domains. Beta is the complex SPP propagation constant, and gamma D and gamma M represent the positive real numbers that describe the decay of the field away from the metal dielectric interfaces. Okay, for the equation 5 to 7, we can see the tangential components of the electric and magnetic fields and the normal component of the electric displacement field that are continuous across the metal dielectric boundary. Therefore, we see these equation. For equation 8 and 9, as we know, there is no external charge here, and the permittivity is constant inside the respective metallic and dielectric domains. It means the divergence of electric field is equal to 0 must hold inside the two regions. Combining this condition with equation 2 and 4 gives the following two equations, which means 8 and 9. And subsequently, if those two equations are combined, we can get the simple relation. We can see gamma d is per epsilon d is equal to minus gamma m divided by epsilon m. From 8 to 10, it can be clear that why SPPs only exist between a dielectric having a positive real part of the permittivity and a metal having a negative real part of the permittivity. To have the field decay in the y direction, both gamma d and gamma m must be positive, which means that the permittivity epsilon d and epsilon m must have opposite sign. To derive the expression for the propagation constant, we can write the Helmholtz equation, as you can see, equation 11, and the propagation constant by the related equations. Okay, here we can see the lambda SPP, which is mean the wavelength of surface plasmon polariton, which is related to real of beta that considered in equation 12 to 14. Okay, we can start the simulation. For the simulation, I choose COMSOL 6.2. In the model builder, I go to the model wizard. In model wizard, I choose the 2D. Then I go to optics and wave optics. In wave optics, I choose electromagnetic waves frequency domain, EWFD, and I add it. Then I click on the study and I choose the preset study for selected physics, and you can see the study here. I choose the boundary mode analysis and I click done. Okay, and here in the global definition, I go to parameters. I define some parameters, for example L equal to 2 micrometer, which means the simulation domain length and h is equal to 3 micrometer, and LDA 0, which means the wavelength 400 nanometer, and F0, that is equal to C const divided by LDA 0. The LDA 0, it means the wavelength of the operation, and the F0, it means the frequency. Okay, in the geometry, I go to geometry part, I click right on it, I choose rectangle. In rectangle, in the width text, I type the L, and in the height, I type the H. And I go to layers, I expand it, and then for layer 1 I write half of H, and I build all objects. We can choose it as the maybe as the center, or maybe as corner. It depends on ourselves. I choose a corner here, and I choose form union to build all. Okay, in the following I go to material, and I choose the material from the library. I go to optical. In optical, inorganic material, I choose AG silver. In AG silver, I choose experimental data, bulk, and in the experimental data, I choose Johnson and Christie from the first one. I choose this, I double click on it. Okay, then I go to a blank material, for choosing air. I go to blank material, and I type it as air. Okay, and for AG region, I choose the bottom, and for A I choose the top. As we can see, the refractive index, real and imaginary part, is selected from the material library of the COMSOL, and for air we must type N and K. As we know, the N is 1 for the air and the K is 0. Okay, In the electromagnetic part, I click right on it, and first I group by a space dimension. I click right on the boundaries. I choose the port. Into port, I choose the left side and I choose the default values, 1 watt per meter, and for the type of port I choose the numeric, and the mode phase I choose the 0 degree or 0 radian for the mode phase, and I click on boundaries and I choose another port as a port 2. In port 2 I choose the numeric, and in port 2 I choose a numeric for the right side, and I off the wave excitation and the numeric port, and also as the same the mode phase is equal to 0. Okay. In the continue, I go to the study step 1. In the study step 1, we can see the boundary mode analysis. And in this study setting, we can see the transform and other properties that we can change it. And in the mode analysis frequency, I type F0, which we defined in the parameter. And for mode search method, I can type the around shift maybe, or rectangle. I choose around shift here, and desired number of modes also can be changed. I can choose different values, and also for the search for mode around the shift, I can choose another different values. For example, I choose a 5, and also the search method around shift, I choose the closest in the absolute value. Okay. For boundary mode, we can choose another boundary mode as a boundary mode 2, and to study different analysis. Let me add it by right click on this and duplicating. We have a 2-step. Step 1 boundary mode analysis, step 2 boundary mode analysis of 1. In this one, I choose the port name 2, which means we have analysis on port 2, and for the first we have analysis on port 1. And the mode analysis is frequency is equal to F0, air pack, round shift, and the 5. And the values of linearization point is better to be physics controlled. Okay. In frequency domain, I can choose the F0 in the frequencies and terahertz as the unit. Okay, also we could we can add the parametric sweep. In the parametric sweep, I can add the LDA 0, and I can change the range from 340 to 600 nanometer. Okay, and it's better to check the mesh also. Okay, we choose the frequency domain for the study simulation. Also, I add the parametric sweep, and in I can go to analytic to type. Let me check this. I can go to definition, and in the analytics, I can write the function for analytic 1 for epsilon r in the expression. I write the math 1 that RFI that N RX minus 1I, which means the imaginary part, multiplied to math 1 dot RFI dot NIX two, and we can choose a lower limit for the lower and upper limit for the x. Here, let me check the function unit. After running, it will be show us. Let me check the code. NRX minus 1I mat 1 RFI okay. This code was given from the material. Let me show the equation view. We must add the equation view from this, and we can see the equations are available here. And now we can check the mesh. For the mesh, I choose the size. I right click on it, I choose the size, and in the size I choose general physics and I choose custom. For custom, and I choose 50 nanometer, and nanometer 1.3, 0.3 and 1. And for size 1 I choose the boundaries of 1367, 1367, and I choose the custom. For the maximum and minimum element size I choose 25 nanometer, and for minimum element size I choose 0.75. The maximum element growth rate 1.3, and the curvature factor is 0.3, and resolution is 1. And for size 2 I add another size. For size 2 I can choose the boundary 4, and I can choose custom, and in the maximum element size I choose I write this code LDA 0 divided by real SQRT epsilon r LDA 0 1 meter divided by 1 plus epsilon r LDA 0 the divided by 1 meter, and we must add five parentheses divided by 12. It is okay. You can see the black box, which means the code is okay. And let me also use the nanometer unit for the all geometry. It's better, and we can add another option for geometry. I choose free triangular. In free triangular, I use the remaining scale geometry one in x and y, and the control entity is 4 and 4. Tessellation is automatic, and I can build all. Okay, and now we can run the simulation. We can compute the simulation. In the convergence plot, we can see the convergence of the error bar versus iteration number. After the running this simulation, we can plot the transmittance and absorbance, the electric mode field on port 1 and 2, and also SPP dispersion. That gives us the good information about the surface polariton plasmon of this material. Okay, we can see the electric field. In the electric field, we can add the surface, as we can see, and in the surface I can choose the electromagnetic field in the y direction, EY. I can plot it, and also I can choose arrow surface, and in arrow surface I can choose EX and EY. And also the number of 50 and 50. With the scale factor of the arrow type and proportional tail 1e minus 3, and the color is, for example, black, and we can plot it. Okay, and we can also check the parametric solution. We can choose a different wavelength, for example this value, and also the color of the surface, which we can choose for example wave light. Let me check the for example wave light. You can see the wave light here, and in the reflectance and transmittance we can see this figure. The cyan is related to absorbance and the red is related to transmittance, total reflectance and transmittance. And we can remove, for example, R and R total and R port to see better result. T port 2 and A total, it's better. And you can see the absorbance and transmittance. The reflectance is very low, that can be neglected. And also you can see the electric mode field in two different conditions for the port 1 and port 2. Also we can have the SPP dispersion. For this I can go to result, I right click on it, I choose 1D, then I click right and I choose global. In global I can choose a freq, which means the frequency, and multiply it to H const. Then it can be as electron volt. I can plot it. For all, maybe we can choose all frequency, or we can choose a parametric. It's better to see all. I can turn off the legend to see better resolution, and also I can check this as the all solution and the expression as the beta. I can choose EWFD, excuse me, EWFD dot beta 1 radian per meter. It's better, and you can see the analytic SPP dispersion, we can call it. Let me title it as and also we can use a color expression for doing a better model. In the color expression I can write the minus real EWFD dot beta 1 divided by imaginary of EWFD dot beta 1, and also the range of color I can choose from, for example, 0 to 800, and also choose the different color. For example, let me check color table. For example, Verdis, you can see the different color for this plot. And also I can plot it as the, let me duplicate it, and I remove the color, and we can plot it as the EWFD.K0 and we can see the light line. This is light line because we have K0, which means the wave number in the free space equal to 2p divided by LDA or lambda. And for the global tree also we can add the global tree, and in the color expression we can add the different equation to see the different properties. Okay, the simulation is done, and here we choose AG. You can search the other material. I suggest you choose an optical inorganic material. For example, it's better choose aluminum, maybe platinum, iron, and other material, and also gold, and see what will happen for the result of electric field mode, and also the transmittance and absorbance. These will different, and also for the SPP dispersion you can add the frequency multiplied to H versus beta, which means you have the dispersion of bulk. For your material, here is silver. Here we have simulate light line, we have simulated SPP, and we can add analytic that you can see the both of them are the same. Okay, I hope you enjoy this video. Please subscribe to my channel, share my channel to your friends, leave your comments, like my videos. Thank you for caring my advices. Have a good time, take care, goodbye.